Why can't a global superpower like the US or a manufacturing juggernaut like China simply build an extreme ultraviolet lithography machine on their own? The answer explains the most complex geopolitical chess game on Earth. We often hear people refer to ASML as the Dutch company that makes the world's most advanced chip-making machines. But the idea that this is strictly a Dutch creation is one of the biggest misconceptions in modern technology. If you take apart an EUV machine made by ASML and remove all its imported components, all you're left with in the Netherlands is an empty metal frame and control software. A single EUV machine weighs over 180 metric tons, costs up to $350 million, and contains over 100,000 precision parts supplied by more than 5,000 companies across the globe. Shipping just one unit requires 3 fully loaded Boeing 747 cargo jets. ASML isn't a traditional sole manufacturer. They are the world's ultimate system integrator. The EUV machine is actually a global technological coalition where every single critical component is monopolized by a specific nation. So, if we dismantle the most expensive piece of manufacturing hardware on Earth, component by component, who actually owns what? Let's break down the map. Let's start with the most brutal engineering problem in modern physics. How do you generate extreme ultraviolet light at a wavelength of just 13.5 nanometers? That tech didn't come out of Europe. It was born in San Diego, California. The heart of the EUV machine, the light source, was engineered by an American company called Cymer. ASML acquired Cymer in 2013 for $3.1 billion, simply because nobody else on Earth could solve this problem. Here's the breakdown of how this light source works. A high-precision nozzle ejects 50,000 droplets of molten tin per second. Each droplet is roughly 1/3 the diameter of a human hair. As those droplets fall, a high-power American-designed CO2 laser blast hits each tiny droplet, not once, but twice. First, a low-energy laser pulse flattens the tin droplet into a microscopic pancake. Second, a high-energy pulse detonates that pancake with insane energy, vaporizing the tin into a plasma state reaching hundreds of thousands of degrees Celsius. It's that scorching tin plasma that actually emits 13.5 nanometer EUV light. This process happens 50,000 times every single second, around the clock, without missing a single droplet. But the US doesn't just own the light source. It holds another master key: computational lithography software. At the nanometer scale, EUV light bends and distorts when passing through tiny mask patterns. To prevent the light from smudging on the silicon wafer, American software firms, along with ASML's US subsidiary, Brion, use complex algorithms to calculate light diffraction beforehand. They pre-distort the pattern on the photomask so that when the light hits the wafer, it bakes the exact razor-sharp circuit design intended. Add in KLA Corporation, a California giant that completely dominates the metrology and inspection systems needed to analyze wafer surfaces, and the reality is clear. Without American laser physics, algorithms, and inspection gear, the EUV machine would just project useless blur. Now that America generates the light, who directs and focuses it? That's where Germany steps into the ring. EUV light comes with a major physical drawback. Air absorbs it, and glass absorbs it completely. That means traditional refractive glass lenses are totally useless here. To bypass this wall, the legendary German optics titan, Carl Zeiss, SMT, engineered a system of multi-layer reflective mirrors. Instead of letting light pass through a lens, Zeiss bounces the EUV beam off a series of ultra-precise mirrors arranged in a zigzag pattern. Each mirror is coated with 40 to 50 alternating layers of molybdenum and silicon, each layer just a few atoms thick. The surface flatness of these Zeiss mirrors pushes the absolute limits of physical law. As Zeiss engineers put it, if you scaled one of these mirrors up to the size of the entire continental United States, the tallest bump on the surface wouldn't be higher than 1 millimeter. A stray particle of dust on these mirrors would act like a mountain blocking the light beam, ruining millions of dollars worth of microchips. And Zeiss isn't Germany's only piece on the board. Enter TRUMPF, an industrial laser titan. To power that American light source, TRUMPF built a 30-kilowatt CO2 laser amplifier weighing 17 metric tons, made of 457,000 individual parts and over 4.5 miles of internal cabling. It amplifies the laser pulse by more than 10,000 times. It is, unequivocally, the most powerful industrial laser system ever created. Without German optical glass and laser engineering, that American EUV light would be impossible to drive or focus. The light is generated in America and focused by Germany. But what does it actually print onto, and how do you verify the circuit pattern before firing the laser? This is where Japan wields a chokehold monopoly. Consider a company most people outside the semiconductor industry have never heard of: Lasertec Corporation, based out of Yokohama, Japan. Lasertec currently holds a 100% global market share in EUV actinic blank inspection machines. Photomasks contain the blueprint for billions of transistors. If there's a flaw as small as a couple of nanometers on that mask, the EUV-C machine will replicate that error onto millions of chips. No chipmaker, whether it's TSMC, Intel, or Samsung, will load a photomask into an ASML machine without running it through a Lasertec scanner first. Then, there are the raw photomask materials. Two Japanese companies, Hoya Corporation and AGC Inc., supply nearly the entire global market for ultra-pure quartz EUV mask blanks. And once that EUV light finally strikes the silicon wafer, the wafer must be coated with a specialized, highly reactive chemical, EUV photoresist. Three Japanese chemical conglomerates, JSR Corporation, Shin-Etsu Chemical, and Tokyo Oka Kogyo, control over 90% of the global EUV photoresist market. Back in 2019, when Japan briefly restricted photoresist exports to South Korea, it paralyzed Samsung's chip production almost overnight. Finally, Tokyo Electron manufactures the massive track system docked directly to ASML's EUV unit, automatically applying photoresist and processing the wafers before and after exposure. Without Japanese chemicals, mask blanks, and ultra-precise inspection tools, an EUV machine is just a fancy projector with no film and no photo paper. So we have American light, German optics, and Japanese chemistry. But what kind of environment does this process require to operate? The answer, an ultra-high vacuum chamber. Because atmospheric gases like oxygen and nitrogen instantly absorb EUV light within millimeters, the entire light path from the source, off the mirrors, through the mask, and onto the wafer must exist in a near-total vacuum. To pull air out of the system and maintain this environment, ASML relies on the United Kingdom. Crawley-based Edwards Vacuum supplies the sub-fab vacuum pumps and abatement systems for EUV systems. Operating on the sub-fab floor underneath the cleanroom, Edwards pumps evacuate thousands of liters of air per minute while managing toxic hydrogen gas generated from the tin detonation process. Working alongside the UK is Switzerland. Swiss firm VAT Valves is the exclusive supplier of ultra-high vacuum gate valves. These valves open and close in milliseconds to isolate vacuum chambers without generating a single microscopic particle of mechanical dust. Meanwhile, France provides key ultra-stable power modules, specialized industrial gases like argon and xenon from Air Liquide, and advanced thermal insulation materials. With all these world-class components sourced from the US, Germany, Japan, the UK, Switzerland, and France. What does the Netherlands actually do? The Dutch are the master architects. ASML, alongside domestic partners like VDL Group and ProDrive Technologies, solved one of the hardest mechanical engineering feats in history. building the wafer stage. The silicon wafer doesn't sit still during printing. It has to move rapidly beneath the EUV light beam to print hundreds of individual chips across its surface. The magnetic levitation wafer stage, engineered in the Netherlands, accelerates faster than a fighter jet launch, moving at extreme speeds, yet stopping with a margin of error under 0.25 nanometers, literally smaller than a single atom. The Dutch don't manufacture the mirrors, the lasers, or the photoresist, but their system integration, software coordination, and nanometer kinetics turn hundreds of thousands of isolated components into a flawless symphony. And this brings us back to our opening question. Why can't the US or China just replicate this machine on their own? Because building an EUV system isn't just about throwing hundreds of billions of dollars at a factory. To go completely solo, a single nation would have to simultaneously master German precision optics, Japanese specialty chemistry, American plasma physics, Dutch high-speed mechanics, and British vacuum engineering. You aren't just trying to copy a machine. You're trying to replicate 40 years of specialized, cross-border R&D. The EUV machine isn't just a triumph of modern engineering. It is the most impenetrable geopolitical fortress on the planet. A machine built by the world, for the world, that no single nation can ever truly own alone. Which part of this global supply chain surprised you the most? Drop your thoughts in the comments below. Thanks for watching, and don't forget to like and subscribe for more deep dives into the technology shaping our world.